Okay, now today in our machine lecture, we will solve some numerical based on losses and efficiency in three-phase induction motor. So for the three-phase induction motor, we already discussed the power stages. So simply the power input to the three-phase induction motor is P1, P1, which is the three-phase power, which is equal to root 3 VL IL cos theta. So this is the input power, and it will give the some stator copper loss and iron loss. So stator copper loss and iron loss. After subtracting, we obtained the rotor input. If you subtract it, the rotor copper loss, rotor Cu loss, then we find gross mechanical power developed by motor, and which is denoted by Pg. And if you subtract it, some windage and frictional loss, we'll get net power output at shaft or TSH, shaft torque. Okay. So this is the flow, power flow diagram, or power flow simply in this fashion. No doubt we can understand with this one. Say, instead of this one, we use this to understand the power stages. So this is the motor input, that is the P1, stator copper loss. This is subtract. If you subtract the motor input, stator copper loss from the motor input, we get the rotor input P2. Now rotor copper loss, if it is subtracted from the P2, gross mechanical power developed by motor, and after subtracting windage and frictional losses, rotor output, that is a P out, or we can say that shaft power, isn't it? Similarly, if someone knows the nameplate rating, that is the output rating of the motor, by adding windage and frictional loss, we get gross mechanical power developed. If rotor copper losses get added in the gross mechanical power, it is nothing but the rotor input, and rotor input plus stator copper loss plus iron losses is nothing but the motor output, motor input. So from this one, we do some numerical based on this topic. Say, for example, the numerical is like that. The power input to three-phase induction motor is 40 kilowatt. The stator losses total 1 kilowatt, and frictional and windage losses total 2 kilowatt, and slip of motor is 4%. Find mechanical power output, rotor copper losses per phase, and efficiency. So here the data is given as a three-phase induction motor. Is the stator motor input, power input, that is a P1, which is nothing but that power input is 40 kilowatt motor input. Is total stator losses. Total stator loss. This stator loss is stator Cu loss plus iron loss. It is equal to 1 kilowatt. Whereas windage and frictional loss, which is given as a 2 kilowatt. Slip of motor is here 4%. Find the motor output and rotor copper losses per phase. Okay, so we will start solving solution. So input, motor input, is equal to 40 kilowatt. Therefore, output of stator, because stator copper losses are known, output of stator is motor input minus stator losses. So it is 40 minus 1, 39 kilowatt. Now output of stator is nothing but the rotor input. So rotor input via air gap. So rotor input. As we know that the relation rotor copper loss, rotor CU loss is equal to slip multiplied by rotor input. The rotor input. Now slip is given. Rotor input we already calculated over here. So it is 4%. So it is 0.04 multiplied by 39 kilowatt. It is equal to 1.56 kilowatt. 1.56 kilowatt. No doubt it is the total copper loss, total rotor copper loss are there. Therefore, rotor copper loss per phase is equal to 1.56 divided by 3 is equal to 37.4 watt. The rotor copper loss is equal to this much, and therefore rotor copper losses per phase, we want to calculate rotor copper loss per phase. So it is equal to 1.56 divided by 3. So it is 0.52 kilowatt. This is the first parameter we found it. Now second, we want the mechanical power output. Okay, so for this one, we have one more relation, that is a gross mechanical power developed divided by rotor CU loss is equal to 1 minus S upon S. So from this one, gross mechanical power we can calculate, but we want the motor output. So we can calculate the gross mechanical power developed by this formula, or it may be a gross mechanical power is equal to rotor input minus rotor CU loss. Okay, so simply gross mechanical power is the rotor input minus rotor copper losses. So here the rotor input already, we have calculated. It is a 39 kilowatt minus rotor copper losses is 2 kilowatt. Or how much it is given? The rotor copper loss, yes, we have calculated is 1.56 kilowatt. So it is equal to 37.4 44 kilowatt. So this is the gross mechanical power developed. So therefore, power output is equal to gross mechanical power minus windage and frictional loss. So it is equal to 37.44 minus 2 kilowatt. So it is equal to 35.44 kilowatt. So this is the net power available at a shaft. Therefore, efficiency is equal to power output divided by power input multiplied by 100. It is equal to 35.44 divided by 40 kilowatt into 100. So efficiency of motor is 88.6%. So simply, if you remember the block diagram, that is the power stage block diagram, it is quite simple to calculate efficiency, regulation, efficiency, losses, torque, anything we can calculate it. One more numerical, we will solve it by same relations. The numerical is like that. The rotor EMF of 3-phase 440 volt 4-pole 50 hertz induction motor makes 84 complete cycle per minute. When the shaft torque is 203.5 kilowatt, 203.5 Newton meter, calculate HP, that is horsepower of the motor. So now here number of cycle is given of the rotor circuit. Number of cycle per minute, it is equal to, is given 84. It means that the EMF induced in the rotor circuit, which have the frequency number of cycle per minute, is 84. Now the number of cycle, this is one data is given. Second data is that number of pole P is equal to 4 and supply voltage V is equal to 440 volt. Anything is given? Yes. The torque, shaft torque, TSH is equal to 203.5 Newton meter. This data is given. Okay. So it is simple. So first of all, we will calculate the number of cycle per second is equal to 84 divided by 60 is equal to 1.4, and number of cycle per second is nothing but the hertz. So it is nothing but frequency of rotor EMF. Okay. So we know our equation, rotor frequency is equal to slip multiplied by supply frequency. That is F dash is equal to S into F. Now the number of cycle of rotor frequency of rotor EMF, it is nothing but F dash. So therefore 1.4 is equal to 1.4 is equal to the slip is, how much slip is given? Here the slip Slip is here the 50 hertz frequency is there. Three-phase induction motor. Supply frequency F is equal to 50 hertz. So multiplied by slip into 50. So this value of slip is equal to 0.028. That is, it is 2.8%. Now, once we calculated or we know this value of slip, it is quite possible, or we can calculate the speed of motor. The synchronous speed of motor Ns is equal to 120F upon P. So here it is 120 multiplied by 50 divided by 4-pole motor. So the synchronous speed of motor is equal to 1500 RPM. Now the rotor speed or motor speed we can consider simply as a motor speed N is equal to 1 minus S into Ns. Since Ns minus N upon Ns is equal to slip. So from this one, 1 minus 0.028 multiplied by 1500 RPM. So rotor speed or motor speed simply, it is equal to 1458 RPMs. Now, shaft torque TSH, it is given 9.55 into power output divided by speed. This is the general torque of the motor. Now here the torque is given 203.5 Newton meter. No doubt it is in Newton meter. 9.55 P out we will calculate, and speed is 1458 RPM. So therefore output of motor equals to output of motor. From this one we can calculate output of motor, and output of motor, output in HP is equal to P out divided by 745, that is 1 HP is equal to 745 watt. So output of motor in HP is equal to 41.6. So this is the second numerical by this energy or the power flow diagram. The third numerical is such that the input to three-phase induction motor is 65 kilowatt and the stator losses is 1 kilowatt. Find the total mechanical power developed and the rotor copper losses per phase if the slip is 3%. Calculate in terms of mechanical power developed the input to the rotor when the motor yields full load torque at half speed. One more numericals we have. Say the motor input to 6-pole 3-phase 50 Hz induction motor is 42 kilowatt. The speed is 970 RPM. The stator losses are 1.2 kilowatt. Frictional and windage losses are 1.8 kilowatt. Find 1 slip, 2 rotor output, 3 rotor copper losses, and fourth is the slip. Fourth is the frequency. So this is the data given. It is a 6-pole motor. P is equal to 6, 3-phase, 50 hertz, 50 hertz induction motor. And power input to this motor is 42 kilowatt. Whereas the speed of motor is equal to 970 RPM. The stator losses are 1.2 kilowatt. Stator losses is equal to 1.2 kilowatt. And windage and frictional loss is 1.8 kilowatt. So simply here say here in this motor input is P1. Here stator CU loss plus iron loss. So it is get subtracted. Now after that we will get the rotor input. Now rotor input, it is the rotor CU loss. And rotor CU loss, it is the gross mechanical power developed. Here we will subtract the windage and frictional loss. So finally, we get output of motor. So it is a P out. Okay. So now which is given? First of all, we will start from the relation. Synchronous speed is equal to 120 F upon P. So here it is 120 multiplied by 50 divided by number of pole is 6, so 1000 RPM. So synchronous speed we know the rotor speed, so we can calculate the slip is equal to ns minus n upon ns into 100. So it will give the percentage slip, and percentage slip is 3%. So putting this value 1000 RPM minus 970. So this is a 3% slip is there. Now we know that the relation rotor CU loss is equal to slip multiplied by rotor input. But how to calculate the rotor input? Rotor input is nothing but motor input minus stator copper loss, stator losses. So rotor input is equal to motor input minus stator losses. So here motor input is 42 kilowatt minus stator copper loss, stator losses total including iron loss, it is 1.2. So here the rotor input become 40 kilowatt is equal to 42 minus 1.2. So it is how much? It is 40.8 kilowatt. Now rotor copper loss from this one. Therefore, rotor CU loss is equal to slip. It is 3.03 into 40.8. So it is around 1.224 kilowatt. Now, but here it is asked to calculate rotor copper loss. Okay, so rotor copper losses are this one. It is, or you can write as 1224 watt. Now rotor, this is the one rotor copper losses we have calculated. It is here we can write it is 1224 watt. Whereas input of the motor is 42 kilowatt, stator copper loss is 1.2. So rotor input become here of 40.8 kilowatt. All values are in the kilowatt. Now rotor copper losses, it is 1.2 kilowatt. So this, if it is subtracted from 48, we get the gross mechanical power. So here gross mechanical power is equal to rotor input minus rotor CU loss, copper loss in the rotor circuit. So it is 40.8 minus rotor copper losses are given or not given. Yes, already we have calculated. It is 1.22, 1.224, and it is equal to gross mechanical power is equal to 39.57 kilowatt. Or we can calculate by the formula as rotor CU loss divided by gross mechanical power is equal to S upon 1 minus S. So either with this formula, or we can also calculate rotor by other formula. It is a rotor CU loss, copper losses in the rotor divided by rotor copper losses divided by gross mechanical power developed is S upon 1 minus S. But anyway, but it is quite simple and advantageous to calculate with the help of this power stresses diagram. So it has become more generalized to calculate any type of data for the three-phase induction motor. Now the gross mechanical power developed. Now here the gross mechanical power developed is equal to 39.57 kilowatt, whereas the windage and frictional loss is given. It is 1.8 kilowatt. So if you subtract 1.8 kilowatt from the 39.5, we get the power output to this motor. So P out or motor output is equal to the gross mechanical power minus windage and frictional loss. So which is equal to 39.5 minus 1.8. So it is 1.57, 1.8 kilowatt. It is equal to 37.77 kilowatt. So this is the motor output. So here the motor output, this comes to know 37.77 kilowatt. So this is the output and this is the input. Now the efficiency of motor is equal to 37.77 divided by 42 kilowatt input of the motor multiplied by 100. So the efficiency of motor is 89.9%. So in this way, many more numericals can be calculated by power stages in the three-phase induction motor.